Welcome back to the course Rocket Propulsion offered by EDAL Systems. In today's class, we will discuss about thrust chambers. So the index for today's class is that first we will look out for injectors. So what are injectors and what is their purpose, the function, what are several injector performance parameters. Then we will see combustion chamber and nozzle, in which we will discuss about the heat transfer distribution and different cooling methods for combustion chamber and nozzle. Then we will see about thrusters. So what are thrusters, their advantages, disadvantages, their special features, why they are used, and different types. Then we will see different materials and fabrication processes for this thrust chambers. So each component wise we will see what all materials are used, what cooling method is used for those components. And lastly we will discuss about random variable thrust. So why this random variable thrust is necessary in a rocket engine and how we can achieve that. We will discuss everything in upcoming slides. So let's begin. So the thrust chamber is the key subassembly of a rocket engine. So we have seen a rocket engine consists of several parts based on the propellants, that is solid, liquid, then hybrid, electric. So for a rocket engine, mostly a liquid propellant rocket engine, the thrust chamber is nothing but a subassembly which consists of an injector, a combustion chamber, and a converging diverging nozzle and some mounting provision. So basically in this thrust chamber, the propellants, the fuel and oxidizer which we are using in liquid form, they are metered, then injected, atomized, vaporized, then mixed and burned to form hot reaction gas products, which in turn are accelerated and ejected at supersonic velocity. So we have seen this in liquid propellant rocket engine topic, that this is the complete combustion process of propellants inside the engine, where the propellants are injected, then atomized, vaporized, and then mixed together to form hot reaction gases, and then they are accelerated to high supersonic velocities. So this area where the combustion happens and the thrust is generated is basically called the thrust chamber for a rocket engine. So the rocket thrust chamber assembly has an injector, a combustion chamber, and supersonic nozzle and some mounting provisions. And all these components have to withstand the extreme heat of combustion and the various forces including transmission of thrust force to the vehicle. So the structure should be such strong that it should withstand all such heat loads, the stresses, the strains which are acting with this complex combustion reaction as well as the thrust generation which is happening in the nozzle. Then there is also an ignition system if non-spontaneously ignitable propellants are used. Some engines may use non-spontaneously ignitable propellants, so in that case we will need an ignition system. Some thrust chamber assemblies also have integrally mounted propellant valves and sometimes a thrust vector control device. So based on the applications, the components will change, but the classic or the conventional configuration for a thrust chamber includes an injector, the combustion chamber, and a nozzle. So moving on to the injectors, we will first discuss what are injectors. So the function of an injector are similar to those of a carburetor of an internal combustion engine. So we know that a carburetor is a device that mixes air and fuel for internal combustion engines in an appropriate air-fuel ratio for combustion. So the same work is for the injector in the thrust chamber. So it has to meter the propellants, then it has to allow them to flow into the combustion chamber. So the injectors has to introduce and meter the flow of liquid propellants to the combustion chamber as discussed and cause the liquids to be broken up into small droplets, a process which is called as atomization. So even the atomization process happens in the injector part. Then distribute and mix the propellants in such a manner that a correctly proportional mixture of fuel and oxidizer will result with uniform propellant mass flow and composition over the chamber cross section. So injectors are called the carburetors for rocket engines. So the same way it has to meter the propellant flow and it has to then break up into small droplets and then it has to distribute inside the combustion chamber in such a manner that in a correct proportion the air and fuel mixture is given for the entire chamber cross section. So here to the right we can see a real injector, how it looks like. So it is a doublet injection pattern type injector. So we'll see what all these types of injectors are there in upcoming slides. So the individual locations on the injector faces are called as injector elements. So here in the injector image, here we can see the small ports are there. So these ports are called as injector elements which are present on injector face. So this complete face circular plate which we see on the top of this injector, that is the injector face, and here these small pores are there. So these pores are called as injector elements. So there are two basic design approaches for admitting propellants into the combustion chamber. So there are basically two types of these injectors. One is hole injection elements and the second one is spray injection elements. So in hole injection elements, it uses a set of propellant jets going through a set of holes in a pattern on the injector face, while for spray injection elements, it uses cylindrical injection elements which deliver a conically shaped spray of propellants into the combustion chamber. So both uses this different kind of injection elements in their configuration based on which they are used for several applications. So we'll discuss these in detail. So first we will discuss about hole injection elements, in which there are two types. So first one is doublet impinging stream type. So even in figure we can see there are fuel manifolds and oxidizer manifolds and injector face we can see. So different holes are present and the impingement points are given. So at impinging points of fuel and oxidizer, they are mixed together because of these holes. The triplet impinging stream type is the next version of the doublet version, where three different holes are impinging the flow at a one single location. So in this type, multiple hole injectors are commonly used with oxygen hydrocarbons and storable propellants. For unlike doublet patterns, the propellants are injected through a number of separate small holes in such a manner that the fuel and oxidizer streams impinge upon each other. So impingement from thin liquid fans and aids atomization of liquids into droplets, also aiding distribution. So this kind of doublet impingement helps in mixing because the fuel and oxidizer are mixed at their impinging points. Now the next type, that is non-impinging or shower head injectors, which employ non-impinging streams of propellants usually emerging normal to the face of injector. It relies on turbulence and diffusion to achieve mixing. So here we can see each fuel manifold has its own impinging point and oxidizer manifold has its own impinging point. It is a very simple and the oldest injection element type. That's why it is called as shower head injection, where we see that in our washroom we use the water shower for bathing. So the water droplets which come, they are in a straight position and they do not mix with each other until it reaches a certain location. So same happens in the spray head injector type, which was used in German World War II with V2 rocket, which was the very oldest rocket used. So this type is no longer used because it requires large chamber volume for good combustion. And as it relies on turbulence and diffusion to achieve mixing, it is very difficult to use this kind of injection type in today's rocket engines. So moving on to the next type, that is spray injection elements. So here we have again two types. That is, first is sheet or spray type injections. So it gives cylindrical, conical or other types of spray sheets. These sprays generally intersect and thereby promote mixing and atomization. The conical sheets break up into droplets which are then vaporized. The size distribution of droplets from spray injection elements is usually more uniform than with impinging streams from holes. So here in figure we can see a metering orifice is given from which the propellants will enter and a conical spray sheet will be formed which will break up into droplets, which thereby promotes mixing and atomization. Then the next type here is the coaxial hollow post or spray injectors. So it has been used for liquid oxygen and gaseous hydrogen injectors by most domestic and foreign rocket designs, and it is shown in sketches D and E of the figure. So here in D and E figure we can see that the tangential injection orifices are given for both the category, where a cone is formed and coaxial flow is allowed in this kind of injection. So we will see what are the injector performance parameters for this kind of injectors to work properly. So complete theory relating injector design parameters to rocket performance and combustion phenomena has not yet been devised, and therefore the approach to the design and development of liquid propellant rocket injectors has been largely empirical. These factors which we will discuss now are different for injectors where both propellants are liquid, such as say nitrogen tetroxide and hydrazine, or where one propellant is liquid and the other is gaseous, as with LOX gasified liquid hydrogen. So some of the parameters are listed here are the propellant combination. So what fuel and oxidizer we are using as the propellants, then the transient conditions, then injection, element pattern and orifice size, different hydraulic characteristics, then the heat transfer, the structural design, then combustion stability. So we'll discuss each of these parameters in brief. So first one, that is propellant combination. Particular combination of fuel and oxidizer affects such characteristics as the relative chemical reactivity, the ease and speed of vaporization, the ignition temperature, the diffusion of hot gases, the volatility or the surface tension. So each propellant has its own characteristics based on which, when it is combined with the other propellant, it will give us some different properties. So these all propellant combinations which we are using, based on their reacting characteristics, it may affect the injector performance as well. Then we have transient conditions. So starting and stopping may require special provisions, that is temporary plugging of holes, accurate valve timing, insertion of pepper cups over holes to prevent entry of one propellant into the manifold of the other propellant, which was done in German A4 or V2 thrust chambers or for check valves. So to reach these transient conditions for any rocket engine, we may have to follow any of these techniques where we have to stop the injector flows. So this may affect the injector performance. Then the next factor, that is injection element pattern and orifice size. So the orifice which we are using, what is its size, and the element patterns on the injector face may also affect the injector performance. So with individual elements of holes or sprays in the injector plate, this appears to be an optimum performance and heat transfer condition for each of the following parameters, that is orifice size, angle of impingement, angle of resultant momentum, distance of the impingement locus from the injector face, number of injection orifices per unit of injector face surface, flow per unit of injection orifice, and distribution of the orifices over the injector face. So these are the different factors of injection element pattern and orifice size which will affect the injector performance. The next parameter, that is hydraulic characteristics. So the orifice type and the pressure drop across the injection orifice determine the injection velocity, and a low pressure drop is desirable to minimize the weight of the feed system or the pumping power. So to minimize the weight of the feed systems or the pumping power inside a liquid propellant rocket engine, generally we need a low pressure drop, because this pressure drop across the injector orifice determines the injector velocity. So high pressure drops are used to increase the rocket's resistance to combustion instability and enhance atomization of the liquids and improve performance. Then the next one, that is heat transfer. So injectors influence the performance and the heat transferred in rocket thrust chambers. So even the injectors influence the performance and heat transferred in thrust chambers, even though their function is very less compared to combustion chamber and nozzle. So low heat transfer rates have been obtained when the injection pattern resulted in an intentionally rich mixture near the chamber walls and when the chamber pressure is low. In general, the higher performance injectors have a higher heat transfer rate to the walls of the combustion chamber, the nozzle, and the injector face. So the last two factors which we will discuss for injectors is first structural design and combustion stability. So first we will discuss about structural design. So the faces of most modern injectors are flat and must be reinforced by suitable structures, which nevertheless should provide no obstruction to the hydraulic manifold passages. The structure must also be sufficiently flexible to allow internal deformation caused by heating the injector face with hot combustion gases or cooling of certain flow passages by cryogenic propellants. Then the injector design must also provide for positive seals between fuel and oxidizer manifolds and the sealed attachment of the injector to the chamber. So good seals should be provided for each fuel and oxidizer manifolds, because an internal leak can cause manifold explosion or internal fires. Then the last parameter, that is combustion stability. So the injector hole or spray pattern, impingement pattern, hole or spray element distribution, and pressure drop have a strong influence on combustion stability, sometimes are much more resistant to pressure disturbances. So if any of the following properties or parameters are altered, then it may have a good impact on the pressure disturbances. So the resistance to vibration is determined experimentally, and often special anti-vibration devices such as baffles or resonances cavities are designed directly into the injector. So with the experiments, the resistance to vibration is determined, and special anti-vibration devices such as baffles or resonance cavities are designed directly into the injectors. So to provide the combustion stability for a combustion chamber, these all techniques are employed inside the injector itself. Moving on to the next title, that is manufacturing of injectors. So we'll see how these injectors are manufactured. So the original method of making injection holes was to carefully drill them and round out to chamfer their inlets, and this method is still being done today. So very simple method, that is just drilling the holes and then round out or chamfer their inlets to remove the surface roughness or irregularities present. But it is difficult to align these holes accurately for good impingement and to avoid bursts and surface irregularity. One method that avoids these problems and allow a large number of small accurate injection orifices is to use multiple etched, very thin plates, which are often called as platelets, that are then stacked and diffusion bonded together to form a monolithic structure. The photo-etched pattern on each of the individual plates or metal sheets then provide not only for many small injection orifices at the injector face but also for internal distribution or flow passages in the injector, which sometimes also for a fine filter inside the injector body is used. The platelets can be stacked parallel to or normal to the injector face, and the finished injector has been called the platelet injector and has been patented by the Aerojet Propulsion Company. So this way the problem of surface bursts and surface irregularities has been removed out by this technique. Then next we will discuss about combustion chamber and nozzle. So we know that inside a combustion chamber of a rocket engine several processes happen, but the main thing is the mixing, the atomization, vaporization and chemical reactions forming turbulence and generating thrust. So the combustion temperature is much higher than the melting points of most chamber wall materials. Therefore, it is necessary either to cool these walls or to stop rocket operation before the critical wall areas become too hot. If the heat transfer is too high and thus the wall temperatures become locally too high, the thrust chamber will fail. Spherical chambers give the least internal surface area and inert mass per unit chamber volume, but they are very expensive to build and several have been also tried. Today, almost we all prefer a cylindrical chamber or slightly tapered cone frustum with a flat injector and a converging diverging nozzle. So what kind of combustion chamber volume and shape we should go for? So there are several evaluating parameters based on which we have to select the volume and shape for the combustion chamber. So first one is that the volume has to be large enough for adequate atomization, mixing, evaporation and complete combustion of propellants. So the volume should be good enough that these all processes happen inside it. So the chamber diameter and volume can influence the cooling requirements. If the chamber volume and chamber diameter are large, the heat transfer rates to the walls will be reduced, the area exposed to heat will be large. Then all inert components should have minimum mass. So there should be low mass, but volume should be good enough that all the processes happen inside it gently. Then the manufacturing considerations favor a simple chamber geometry, such as a cylinder with a double cone, bow tie shaped nozzle, low cost materials, and simple fabrication process. And the fifth point, that is a large diameter but short chamber and or a short nozzle, can allow somewhat shorter vehicle with lower structural inert vehicle mass. Then the last one, that is the gas pressure drop for accelerating the combustion products within the chamber should be minimum. Any pressure reduction at the nozzle inlet reduces the exhaust velocity and the performance of the vehicle. So any pressure drop at the inlet of nozzle will reduce the injection velocity, which is not good for any rocket engine because we need a high injection velocity at inlet such that high values of thrusts are generated. So the preceding chamber considerations conflict with each other. It is, for instance, impossible to have a large chamber that gives complete combustion but has a low mass. Depending on the application, a compromise solution that will satisfy the majority of these considerations is therefore usually selected and verified by experiments. Then we have thrust chamber nozzles. So the converging section of the nozzle experiences a much higher internal gas pressure than the diverging section, and therefore the design of converging wall is similar to the design of the cylindrical chamber wall. Most thrust chambers use a shortened bell shape for diverging nozzle section. Nozzles with area ratios over 400 have been developed and flown. So here to the top right we can see a CD nozzle, that is a converging section is there and the diverging section. Then at the left bottom we have here a bell nozzle. It looks like a bell, that's why it is called as a bell nozzle. Very large nozzle exit area ratios allow a small but significant improvement in specific impulse, particularly at very high altitudes. However, the extra length, extra nozzle mass and extra vehicle mass necessary to house a large nozzle often make this unattractive. So it has its pros and cons when we use a bigger nozzle, that is a bigger diverging section, which will give a significant improvement in specific impulse, particularly at very high altitudes. But again, it will add an extra mass, extra length, which will be a disadvantage. This disadvantage can be mitigated by a multi-piece nozzle that is stored in annular pieces around the engine during the ascent of the launch vehicle and automatically assembled in space after launch vehicle separates and before firing. This concept, known as extendable nozzle, has been successfully employed in solid propellant rocket motors for space applications for about 27 years. So this kind of extendable nozzles are used in solid propellant rocket motors. which is nothing but a multi-piece nozzle that is stored inside the annular pieces around the engine during the ascent, that is during the takeoff or during the firing from the sea level. And then when it reaches in the space, slowly this annular multi-piece will extend and the nozzle will become more extendable. Now we have discussed combustion chamber and nozzle, so how we will see how this heat transfer distribution is there in the thrust chamber. So heat is transmitted to all internal hardware surfaces exposed to hot gases, namely the injector face, the internal chamber, and the nozzle walls. Only 0.5 to 5% of the total energy generated in the gas is transferred as the heat to the chamber walls. The amount of heat transferred by conduction from the chamber gas to the walls in a rocket thrust chamber is negligible. By far the largest part of the heat is transferred by means of convection, and a part, usually 5 to 35% of the transferred heat, is attributed to radiation. The heat transfer intensity in chemical rocket propulsion can vary from less than 50 watt per centimeter square to over 16 kilowatt per centimeter square. The high values are for the nozzle throat region of large bipropellant thrust chambers and high pressure solid rocket motors. The lower values are for gas generators, nozzle exit sections, or small thrust chambers at low chamber pressures. So here we have a figure which is typical axial heat transfer rate distribution for liquid propellant thrust chambers and solid propellant rocket motors. So on x-axis we have this axial distance, and on y-axis we have this heat transfer rate, and it is clear that along the axial distance of any thrust chamber, the most of the heat transfer rates are at the converging section, that is, the peak is always at the nozzle throat or slightly upstream of the throat, and the lowest value is usually near the nozzle exit. So with this kind of heat transfer distribution inside a thrust chamber, there is always need of cooling inside it. So now we will see the cooling of thrust chambers. So the primary objective of cooling is to prevent the chamber and nozzle walls from becoming too hot, so they will no longer be able to withstand the imposed loads or stresses, thus causing the chamber or nozzle to fail. So conventionally there are two types of cooling methods employed, that is first one steady state method, under which we have regenerative cooling and radiation cooling, and the next method, that is transient heat transfer or heat sink cooling method. And the unconventional methods we have is by using a film cooling method or using a thermal insulation. So we'll discuss each of them in brief. So first one, that is steady state method, inside which the heat transfer rate and the temperatures of the chambers reach thermal equilibrium, and the duration is limited only by the available supply of propellant. So the regenerative cooling is done by building a cooling jacket around the thrust chamber and circulating one of the liquid propellants, usually the fuel, through it before it is fed to the injector. This cooling technique is used primarily with bipropellant chambers of medium to large thrust. It has been effective in applications with high chamber pressure and high heat transfer rates. Also, most injectors use regenerative cooling on their hot faces. So in this kind of cooling, a cooling jacket around the thrust chamber is created by circulating one of the liquid propellants, usually the fuel. And the next method of cooling under steady state is the radiation cooling, in which the chamber and or nozzle have only a single wall made of high temperature materials such as niobium or molybdenum. When it reaches thermal equilibrium, this wall usually glows red or white hot and radiates heat away to the surrounding or to empty spaces. So here the material which is used itself will indicate if it has reached its thermal equilibrium. And then it will start to glow red or white hot, then it will radiate the heat away to the surrounding or to the empty space. So radiation cooling is used with bipropellant and monopropellant thrusters and for diverging nozzle exhaust sections in large thrust chambers. This cooling scheme has worked well with lower pressure chambers, that is less than 250 psi, and moderate heat transfer rates. So this was about the steady state cooling, in which when the thermal equilibrium is reached, these kind of cooling are allowed. But what when it does not reach thermal equilibrium? That's when it comes transient heat transfer, which is also called as heat sink cooling. So the thrust chamber does not reach a thermal equilibrium and temperatures continue to increase with operating duration. The heat absorbing capacity of the metal hardware determines its maximum duration, which is usually short, a few seconds for an all-metal construction. So the rocket combustion operation has to be stopped just before any of the exposed wall reaches a critical temperature at which it could fail. This method has mostly been used with low chamber pressures and low heat transfer rates. The heat sink cooling of the thrust chamber can also be done by absorbing heat in an inner liner made of an ablative material, such as fiber reinforced plastics. Ablative materials burn or erode slowly and cumulative operating durations can be minutes. So these are two conventional cooling methods of thrust chambers. Now we see the other unconventional, that is film cooling and special insulation are supplementary techniques that are used occasionally with both methods to locally augment their cooling capability. So first we will see the film cooling. So this is an auxiliary method applied to chambers and nozzles, augmenting either a marginal steady state or a transient cooling method. Film cooling is a method of cooling whereby a relatively cool thin fluid film covers and protects exposed wall surfaces from excessive heat transfer. The film can be introduced by injecting small quantities of fuel or an inert fuel at very low velocities through a large number of orifices along the exposed surface in such a manner that a protective relatively cool gas film or cool Ponzi layer is formed. Film cooling by itself has been very effective in keeping chamber and nozzle materials from becoming too hot. So it is mostly like the regenerative cooling. And the next one, that is thermal insulation. Theoretically, a good thermal insulation layer on the gas side of the chamber wall can be very effective in reducing chamber wall heat transfer and wall temperatures. However, efforts with good insulation materials such as refractory oxides or ceramic carbides have usually not been successful. They will not withstand differential thermal expansion without cracking or spelling. A sharp edge on the surface, that is cracked or flaked off piece of insulator, will cause a sudden rise in stagnation temperature and most likely lead to a local wall failure. So using thermal insulation can also be very effective in reducing chamber wall heat transfer and wall temperatures, but certain experiments were carried out with the refractory oxides or ceramic carbides which have been successful, but again they will not withstand differential thermal expansion without cracking or spelling. So there will be a crack generated and because of which there can be a local wall failure. Then asbestos is a good insulator and was used several decades ago because it is a cancer causing agent is no longer used. So asbestos was one of the good element, but it is harmful for the humans who are working with it, so it is not used today. Then coating development efforts with rhenium and other materials are continuing. Insulation or heat shields have been successfully applied on the exterior of radiation-cooled thrust chambers to reduce the heat transfer from the hot thrust chamber wall to adjacent sensitive equipment or structures. So this way, with the radiation-cooled thrust chambers, we can use insulation or heat shields on the exterior of these surfaces to reduce the heat transfers from the hot thrust chamber wall to adjacent sensitive equipment or structures. With hydrocarbon fuels, it is possible to form small carbon particles or soot in the hot gas, and that can lead to a carbon deposit on the gas side of combustion chamber or nozzle walls. If it is a thin, mildly adhesive soot, it can be an insulator, but it is difficult to reproduce such a coating. Most designers have preferred instead to use film cooling or extra high coolant velocities in the cooling jackets with injectors that do not create adhesive soot. So there can be a thermal insulation provided for such hot thrust chambers, but again, various techniques again we have to add to prevent crack or soot formation inside the thrust chambers. Then next we will discuss about thrusters. So what are these thrusters? So spacecraft, certain tactical missiles, missile defense vehicles, and upper stage of ballistic missiles often use special multiple thrusters in their small liquid propellant rocket engines. They generally have thrust levels between about 0.5 and 10,000 Newton depending on vehicle size and mission. They are used for trajectory corrections, altitude control, ducking, terminal velocity control in spacecraft, or ballistic missiles, divert or side movement, propellant settling, and other functions. Most operate with multiple restarts for relatively short durations during a major part of their duty cycle. So thrusters are small rocket engines which are used for row thrust applications. So they do have the same configuration as we saw for a thrust chamber, but they are relatively used for small applications only. They can also be classified as first, that is hot gas thrusters, warm gas thrusters, and cold gas thrusters. So hot gas thrusters are used for high performance bipropellant with combustion temperatures above 2600 Kelvin and vacuum impulse of 230 to 325 seconds. Warm gas is used with monopropellant hydrazine with temperatures between 500 and 1600 Kelvin, an impulse of about 180 to 245 seconds. And the last one, that is cold gas thrusters such as high pressure stored nitrogen where the temperature will go from 200 to 320 Kelvin with low specific impulse for around 4 to 120 seconds. So these three type of thrusters are available and they can be used based on their total impulse production for different applications. So the vehicle mission and the automatic control systems of the vehicle often require irregular and frequent pulses to be applied by pairs of attitude control thrust chambers, which often operate for very short periods as low as 0.01 to 0.02 seconds. This type of frequent and short duration thrust applications is also known as pulse thrust operation. There is a performance degradation with decreasing pulse duration for all three types of thrusters because propellants are used inefficiently during the buildup of thrust, and the decay of the thrust when they operate below full chamber pressure and nozzle expansion characteristics are not optimal. The specific impulse really suffers when the pulse duration becomes very short. One way to minimize the impulse variation in short pulses and to maximize the effective actual specific impulse is to minimize the liquid propellant passage volume between the control valve and the combustion chamber. The propellant flow control valves for pulsing altitude control thrust chambers are therefore often designed as an integral part of the thrust chamber injector assembly. Automatic control systems is used to create this irregular and frequent pulses because in some applications short duration thrust is also needed, and with this pulsed thrust generation we are able to achieve such kind of short duration thrust generation. So next we will see materials and fabrication processes used for this thrust chambers. So first we will discuss about materials and their properties. So the choice of the material for the inner chamber wall in the chamber and the nozzle throat region, which are the critical locations, is influenced by the hot gases resulting from the burning of propellants, the maximum wall temperature, the heat transfer, and the duty cycle, and a large variety of materials has been used. For high performance, high heat transfer, regeneratively cooled thrust chambers, a material with high thermal conductivity and a thin wall design will reduce the thermal stresses. Copper is an excellent conductor and it will not really oxidize in fuel-rich non-corrosive gas mixtures. It is often used with oxygen and hydrogen below a mixture ratio of 6.0. The inner walls are therefore usually made of a copper alloy with small additions of zirconium, silver, or silicon, which has a conductivity not quite as good as pure copper but has improved high temperature strength. The material properties have to be evaluated under all likely operating conditions, loads, start conditions, pressure variations, and the like before a material can be selected for specific thrust chamber applications. So this evaluation includes physical properties such as tensile and compressive strength, yield strength, fracture toughness, modulus of elasticity, thermal conductivity, coefficient of thermal expansion, then specific heat, reflectivity, density, etc. Then there are some other important properties also which we will see, that is erosion resistance, little or no chemical reaction with the propellant or the hot gases, reproducible decomposition or vaporization of ablative materials, ease and low cost of fabrication, that is welding, cutting, forming, etc. The consistency of the composition of different batches of each material, that is metals, organic, seals, insulators, lubricants, cleaning fluids, and ready availability and low cost of each material. So properties change with temperature and sometimes they change with little changes in material composition. The temperature where a material loses perhaps 60 to 75% of its room temperature strength is often selected as the maximum allowable wall temperature well below its melting point. Now we will see some of the materials which are used in actual thrust chambers. So for bipropellant thrust chamber with oxygen and hydrogen as their propellants, so in the chamber wall, nozzle converging diverging section walls and thrust region walls at exit region of diverging section of nozzle. The cooling methods used is the fuel cooled, that is regenerative, and the material which is used is copper alloy. While at the injector phase, again the cooling method which is used is fuel cooled, that is regenerative, and for materials, transpiration cooled porous stainless steel phase is used. Then for alternative walls at exit region of diverging section of nozzle, two varieties can be used, that is for cooling, either it may be radiation cooled or transient heat or the sink method which we saw. And for materials, carbon fiber in a carbon matrix or niobium or steel shell with ablative inner liner can be used. Then the next category for experimental thrust chambers, that is very limited duration, only a few seconds, with many kind of propellants. So such kind of thrust chamber with all these components, the material used is low carbon steel and generally it is for very short duration, so no cooling method is provided. For small monopropellant thrust chambers with hydrazine as propellant, so for all the surfaces radiation cooled is used while the material which is used is Inconel or alloy steels, while for injector phase stainless steel is used with fuel cooled, that is regenerative method for cooling. Then the cold gas thrust chambers with compressed air and nitrogen as propellant, which we saw just now. So for all the components, aluminium, steel or plastic is used because it is very small and no cooling is required in such small thrust chambers. Next we will see some fabrication processes. So here in the figure we can see partial section through configurations of the cooling jackets which we discussed earlier. So first one is intermediate corrugated brazed sheet forms the cooling channels and then it is mild channel design. So all the configurations involve curved or doubly curved components and precision fits for good fastening or joining. So the top configuration has an intermediate thin corrugated sheet of metal and has been used extensively in Russia and its predecessor, the Soviet Union. It is soldered together under external pressure in a furnace. It is used in those locations on a thrust chamber where the heat transfer is mild or of intermediate intensity. Then the next one, that is mild slot design, can usually accept the highest heat transfer intensities, and one fabrication technique is to machine nearly rectangular grooves or cooling channels of varying width and depth into the inner surface of a relatively thick contoured inner wall using a high conductivity material such as copper alloy. And the grooves are then filled with wax and by an electrolytic plating technique build an outer wall of a suitable metal such as nickel so as to enclose the coolant channel. The wax is then melted out. So this way these two kind of cooling jackets can be fabricated. Then the rest three are available here. So the third design shows a tubular construction. It has been used extensively in the United States for larger thrust chambers with intermediate to high heat transfer. Individual tubes are shaped to the contour of the thrust chamber, including its nozzle. The round tube shape is altered into nearly rectangular cross sections. The formed and brazed tubes are brazed or soldered together in a furnace, and the outer structural shell or outer bands and also brazed to the assembly. Then the fourth one, that is the corrugated outer wall concept, is perhaps the simplest and often the lightest cooling jacket configuration. It has been used in locations where heat transfer is modest. The last one, the bottom shell, represents a welded construction made of stainless steel. It has a higher allowable maximum wall temperature than a brazed construction. It has been used in nozzle designs and built in Europe. This was all about fabrication techniques for different kind of cooling jackets. Next, moving on to the last topic, that is random variable thrust. So only some applications require a randomly variable thrust from an engine. Examples are descent on a planet or the combat aircraft or upper stage of an anti-ballistic missile. One of the advantages of liquid propellant rocket engines is that they can be designed to throttle or randomly vary its thrust over a wide range during flight. There have been several approaches to achieve variable or randomly reduced thrust, and essentially all the approaches to vary the thrust involve the thrust chamber. One of the early schemes was to use multiple engines or multiple thrust chambers on the same engine and then stop the operation of one or more of them. This random variable thrust is useful in some applications, like when we are descending on a planet or a moon, then for combat aircraft or upper stage of an anti-ballistic missile. And liquid propellant rocket engines are best when we need such kind of alteration because solid propellant rocket motors are very difficult to provide the random variable thrust. And earlier, multiple engines or multiple thrust chambers were used on the same engine, and then the operation of one or more of the engines will be stopped to attain this random variable thrust. So today one can distinguish between two modes of operation and both depend on reducing the propellant flow. First one, that is moderate throttling, and the second one, that is deep throttling. So this moderate throttling is typically over a thrust range of 2 or 3, and this can usually be accomplished without significant design changes to the design. In one application, the thrust is throttled during the ascent of the booster vehicle in order to prevent excessive aerodynamic heating, and in deep throttling, it varies the thrust by a factor of between 6 to 30 for specific engines. It applies, for example, to a planetary landing rocket engine with controlled deceleration. To achieve this deep throttling, the engine requires some special features. With moderate throttling, it can be achieved by simultaneously closing the main fuel valve and main oxidizer valve with matching flow characteristics, or alternatively by slowing down the rotary speed of the turbopumps with a hydraulically matched fuel pump and oxidizer pump. The thrust is almost proportional to the propellant mass flow, and therefore reducing that flow will reduce the thrust. At lower flow, the pressure drop across the injector and the injection velocity will be diminished, the atomization and mixing of the propellants will be somewhat less efficient, and the combustion will be less complete. And the chamber pressure will be reduced of perhaps 1.5 to 9% depending on the specific engine design. This method of varying the thrust is used in a number of booster engines for space launch vehicles. So to achieve this random variable thrust, we just have to reduce our propellant mass flow by some means. So it will vary based on the application or based on the vehicle which we are using. So the summary for today's class is that first we have discussed about fundamentals of thrust chambers, that is what exactly it is in various assembly parts of it and the temperatures it reaches. Then we have discussed about injectors, that is their working principle, and two types, that is low injection elements and spray injection elements. Then we have discussed some of the injector performance parameters and the manufacturing of injectors. So under whole injection type, we have seen doublet impinging type and non-impinging or shower head type. And under spray injection type, we have seen sheet type and coaxial hollow post type injectors. So these type of injectors vary based on how we are giving the impinging for the fuel and oxidizer in whole injection type. While as for the coaxial or the spray injection type, it varies based on how we are forming the cone or how the coaxial flow is happening for the fuel and oxidizer inside the injector. Then we have discussed factors influencing injector performance, that is propellant combination. So based on what propellants we are using, its characteristics will affect the injector performance. Transient conditions, the starting and stopping of the injectors by using several techniques will affect its performance. Then hydraulic characteristics, heat transfer and structural design. Then we discussed the function of combustion chamber and nozzle of a thrust chamber, their volume and shape selection parameters, and the heat transfer distribution in it. So we have seen factors for selection of the shape and volume of a combustion chamber, like the volume should be good enough in which atomization, vaporization, mixing and the reaction, everything should take place, and it should have minimum inert mass. But we have seen that this all factors, they fight to each other, and a compromise has to be made in the selection of the volume and shape of a combustion chamber. For nozzle, we have seen how a CD nozzle, a bell nozzle, and extendable nozzle is used in thrust chambers. Then we have seen heat transfer distribution inside the thrust chamber, which showed that the peak value of heat transfers is mostly at the nozzle throat or before the nozzle throat, just at the inlet of the nozzle. Least value which we get is at nozzle exit region. Then we discussed about two types of conventional thrust chamber cooling methods. That is first steady state method, which included regenerative cooling, that is forming a cooling jacket around the thrust chamber, and then radiation cooling method, where we are using materials which will glow when it is reached thermal equilibrium. Then we have seen transient cooling method, which is called as sink cooling, right, which we have seen that it will never reach thermal equilibrium. Then we have seen film cooling and thermal insulation. Inside thermal insulation, we have seen different techniques used for this thermal insulation. Then we discussed about thrusters, their features, applications, and three types, that is hot gas, warm gas, and cold gas thrusters, where they are used and their advantages. Then we saw problem of pulse thrust operation with thrusters and its remedies. Next, we discussed about materials to be used in thrust chambers and its several physical properties, that is tensile and compressive strengths, yield strengths, models of elasticity, thermal conductivity, density, etc. We discussed the tables which represent various materials used in various parts of different configurations of the thrust chambers. Then we saw different fabrication techniques based on different configurations of cooling jackets. And lastly, we saw the importance of random variable thrust, its features, applications, and means to achieve. So this covers the thrust chamber topic. The references for today's class are present here. In next class, we will start with hybrid propellant rocket engines. Thank you.